Hello everybody and welcome back. So in this video, I'm going to be talking about the differences between the inherent valve characteristic curve and the installed valve characteristic curve. So far we've learned that valves have inherent characteristic curves based on their trim design, and that a valve's inherent characteristic curve will be provided to you by the valve manufacturer. And we've also discussed the three most common types of characteristic curves, which is quick opening, linear or equal percentage. And what they essentially tell you is they tell you what the CV of the valve, or the maximum or the flow rate percentage of the valve would be based on the valve opening percentage that you are operating at. So you could see at different valve characteristic curves, you get a different flow rate percentage for the valve. And obviously at a valve opening of 100%, you get the 100% flow rate that the valve can provide you, which is the maximum CV the valve is rated for. And it's important to note that this chart is provided to you by the manufacturer at a constant pressure drop. And so the system that they use to create this chart is most likely different than the system that you are installing the valve in. And that is why in many cases, the inherent flow characteristic curve does not actually reflect the actual performance of the valve as is installed in your process. So let's talk about the installed valve characteristic curve, because that is what's more relevant to you. So the installed valve characteristic curve reflects the valve's behavior in its final application. So the installed valve characteristic curve would ideally match the inherent valve characteristic curve. However, deviations do occur. And deviations do occur for many reasons. I'm specifying two reasons. However, they mainly occur due to low valve authority across the control valve. So in this course, we're talking about pump sizing and we're talking about transporting liquid. And in most applications, when you're transporting liquid from one point to another, you're using pumps to do that. And so in piping configurations, you're mostly dealing with pumps, and each pump has a characteristic curve. So if you look at an example, for instance, such as a centrifugal pump, you know that we've talked about pump curves, and you could see here's an example of a pump curve for a centrifugal pump. You could see that as the flow rate increases on the x-axis, the pump curve decreases. And this means that the total pressure the pump can provide would actually be a lot less at increased flow rates. So if you look at an example, for instance, let's say you are at point A, which means that you have a piping system and you have a control valve, and let's say the control valve is at 50% opening for the sake of this conversation, and you happen to be operating at this particular flow rate and at this particular pressure drop across the entire system, then the entire piping system, including the control valve. And so the operating point is where the system head curve intersects with the pump curve. And we already know that, and we've solved the case study together. And so what happens is when you want to increase the flow rate in your piping system, you would say, I would just open the control valve a little bit more. And that is correct. However, when you do that, the new operating point will be over here at point B. And in this new operating point, the total head, or the total pressure the pump can provide, is a lot less, because now you have to also consider the pump, which is the source of the pressure and the flow, because essentially pumps can't just give you infinite flow at high pressures. There is always a compromise. So as you're opening the control valve, what you're also doing is you're manipulating the operating point along that pump. And so the pump is able to give you a higher flow rate, but it's going to have to lower the discharge pressure that the control valve will see. And you can immediately see now that the pressure drop across the valve will not be the same from point A and point B. And so with that being said, even though you've manipulated the flow rate, but the common characteristic curve chart that the valve provides you, that the manufacturer provides you, is at a constant pressure. But you do not have that in your application. And that's why when you read this common characteristic curve that the manufacturer provides you, it could be a little bit misleading if you don't recognize the differences between your system and the setup that the manufacturer has used in order to develop this chart. So I can imagine that the manufacturer has a constant inlet pressure and has a fixed outlet pressure, let's say at atmosphere. And what they did is they've changed the valve opening percent, and they've looked at the flow rates relative to the maximum flow rate that the valve would achieve at 100% opening. And based off that, they're able to create this chart. However, in your case, the valve inlet pressure and the valve pressure drop is changing as you manipulate the flow rate. And therefore, you have to be careful when you look at this characteristic curve that the manufacturer gives you. And also, there's another thing that I want you to be aware of, which is the inline losses. So as we've increased the flow rate from point A to point B, the piping friction loss is now a lot higher. And that is because if you remember from my previous lectures, I said, or we've noted down that the friction loss across the piping is related to the velocity to the power of 2, which means that if you increase the flow rate, you've increased the velocity, which means that the contribution of the pressure drop, which goes to the piping system versus the control valve, now has increased. And in fact, actually, the pressure drop in the control valve has reduced. And that's because if we open the control valve more, then we have less restriction across the control valve, which means that now you have a smaller pressure drop across that control valve. So I've annotated this diagram to make it easier for you, or for you to actually see what's going on. So this system curve is just for the piping. So what I did is I calculated the pressure drop across the piping system without the control valve, and I've plotted it over here. So essentially the point A naught over here represents the piping system pressure drop at this particular flow rate. And if we're operating over here, because we have the control valve installed, that means that all of this pressure drop from point A to point A naught is due to the valve's pressure drop. And as you could see at point B, now when you have higher flow rate at a larger valve opening, the pressure drop of the valve, so from point B to B naught, has decreased, even though you have a higher flow rate. And that makes sense, and that's because you just open the valve a little bit more. And when you do that, the valve has less restriction and so less pressure drop across the valve. At the same time, as I've just mentioned, the friction or the pressure drop just for the piping systems, which means all the pipes, all the elbows, the T's, would have a higher pressure drop, and that's because the velocity in them is higher. Now, if we look at the valve authority at point A and point B, so the valve authority at point A, which is essentially the pressure drop of the valve at point A over the system's pressure drop, which is the entire system's pressure drop, which is the piping system plus the control valve at point A, we'll see that that is a lot bigger than the valve authority at point B, because at point B, you have the valve pressure drop is less in relation to the system pressure drop, which is now a lot higher. So you might now have a question, which is, if you cannot completely rely on the common or on the characteristic curve that's provided to you by the valve manufacturer, then what is the installed valve characteristic curve? So that is something that you can plot, and we're going to go through an example in the next video to actually work through some calculations, and I'm going to plot the inherent characteristic curve for the valve that the manufacturer provides, and I'm going to superimpose on that the installed characteristic curve for the valve depending on the context and the application of the example. And you're going to learn how to do it, and you're going to see the differences between them. The differences between them might not be so much, but it's important for you to be aware that there could be differences, and these differences exist because your pressure drop at different valve openings are not the same, and your valve authority at each of these valve openings are not the same. And so it's important for you to be aware of the differences and to be able to recreate or to be able to create your own installed valve characteristic curve, because that is representative of your process. So without further ado, see you in the next video.